I'm Litton Bhandari from Indian Institute of Technology, Vidit, India. So today I'm going to present on the topic a study on defect-induced fatigue failure in SLM Ti6Al4V Alloy. I'll just skip this introduction part as you all know about additive manufacturing. So based upon the previous study, we have established some objective to evaluate the characteristics of Ti6Al4V Alloy powder that we have used for our SLM process, and investigate the effect of the treatment on the microstructure and mechanical properties. And then we did the fatigue performance analysis of SLM Ti6Al4V, and then finally we quantified the defects and investigate the micromechanism of fatigue failures. So this is basically the methodology we have used. We basically fabricated three types of specimens. One is your tensile, another is your fatigue crack growth specimens, CT specimens, and the round specimens. So we have used Renishaw AM400 machine for the same, and for fatigue testing we have used MTS 810 100 kN capacity machine. Coming to the powder characterization, so we use the gas atomized Ti6Al4V powder, which have almost spherical in shape. This shows the distribution, powder distribution, and it has average powder size of 26.17 micron and a standard deviation of 9.7, and you see the powder almost spherical. Then we did some chemical analysis of the Ti6Al4V Alloy powder. So to value the ELI grades, actually we have used the powder of ELI, Salon Distillation grade. To evaluate this, we did ONH analysis of the powder, and we found that the powder that we are using has grade 3 properties. Now, these are the process parameters that we have used. So we have printed the specimen in 60 micron layer thickness, and we know that in this as fabricated specimen have higher tensile resistance. So we did some sort of heat treatment. So heat treatment has been selected based on our previous study. So we did heat treatment at a temperature of 850 degrees centigrade for 2 hours in high vacuum furnace, and we did some sort of surface roughness analysis of our printed sample. So we obtained a surface roughness value of 3.6 micron, and this is our mechanical properties that we got, like yield strength of 808 for heat treated, and UTS of ultimate resistance of the 872. And as fabricated specimens have martensitic structure, and this got decomposed with the heat treatment. This is the erased analysis. Basically, we use the MATLAB-based MTIX module to reconstruct the parent beta grain. So the beta grains are oriented toward the building direction, and this is for the stress lathe. The lathe thickness, the martensitic lathe thickness, basically increase with the heat treatment. Yes. Then we did face identification and texture analysis of as fabricated as well as the heat treated. So I'll just focus on this. So this is the same. We have magnified this region. So basically, a tiny strip of beta has been observed in case of heat treated. So, and whereas in case of S-build, we don't have beta, which is more or less in fraction. That's why we have it. And you see the peaks are wider in case of edge build. That means the solute present in the solvent is higher in concentration, and this shows the presence of martensitic, and it decomposes with the heat treatment. So it's the peak narrows down, and it's not clear there. So you see it shows the 110 grain, and here the intensity, the beta are oriented towards the building direction. And some sort of PM analysis we need to observe the dislocation and all that as built and heat treated. So the qualitative analysis of the presence of dislocation is higher in case of as built as compared to heat treated. Yes. So we did high cycle fatigue of the vertically oriented specimens in this case. So we observe endurance limit at 300 MPa in this case, the process parameter that we have used. These all are tested at room temperature, and where we have used the frequency of 10 Hz in our case. Then we did fatigue crack growth analysis at two different ratio. One is 0.1 and 0.5, and it is tabulated here. So we obtained a threshold of 4.1, 4.7, and even we tried for grade 5, that is a conventional Ti6-4, and in this case we have around 4.25. So almost we are able to obtain a threshold near to the conventional one. And this is the previous analysis of the crack path. So basically this is interlamellar crack propagation. Coming to the damage analysis, all the specimens that have been tested has been analyzed using SLM to evaluate the crack initiation, propagation and fast fracture zone. So you see most of the crack has initiated from the defect region, and these are the few defects that have been observed: porosity, unmelted powder particle and lack of fusion. Similarly, all the specimen contains some sort of defects, and we quantified those defects using some statistical tools. And so this figure shows the root area, that is, we use the Professor Murakami's model. So we evaluated the root area of the crack initiating defect, and the color code shows the root area value, and you see this ring. These are like subsurface defect, and this solid circle is your surface defect. So we plotted against this. So as you see, at a lower root area defect, it has higher life. Then we have used a statistical tool like numbers distribution to plot the crack initiating defects. So we have used reduced variate yi, and it's a natural logarithmic negative numerator of fi, where fi denotes the I upon n plus 1. I is the I we have is the crack arranged in the ascending order. So based on this analysis, we evaluated the maximum crack initiating defect size, root area size, that is 137 micron, and we plotted the Professor Murakami's model here. So this red line indicates the subsurface defect line. Basically, this is the equation that we have used. The gamma is basically the location parameter that has been used here. So you can see in our experimental, we obtained an endurance limit of 300 ampere, but yes, from here, based on the model, we obtained 306 for subsurface, and for surface it's 312. And given that all the crack initiated from the surface and subsurface failure, so this model predicts the values very well. So, like conclusion, so like we have evaluated the powder which has a size of 26.17, and the decomposition alpha prime martensite takes place with the heat treatment, and endurance limit for our case, that the process parameter we have used was around 300 ampere, and most of the crack initiated from the defects that compose of porosity, lack of fusion, unmelted powder particle, and these defects located far away from the surface were not harmful within the investigated range of fatigue lives. So based on the process-induced defect model, we evaluated the extended statistics, and that can predict the fatigue limit of additively manufactured Ti6-4 very well. These are the chronology. Thank you so much.
Now there's time for one or two questions, if any. Okay. Just one.
Yes. You show some Murakami prediction lines. How do you make sure that they are good enough, that the accuracy is good enough, that it's okay for your material?
Actually, we have used the material parameter here, hardness and the location of the defect.
Yeah, but still, hardness is like an assumption that
exactly.
It's a very strong
Murakami model basically can relate the location of the defect and area and actually. Yes, some more parameter to evaluate, but in our case, we have used this same model where the predicted life has been correlated with the hardness.
yeah. Okay, Okay, so yeah, it's very hard to state that this is a good model for this material. It's like I think you need more data.
Okay.
Like to put some experimental points on that Kitagawa diagram to
Oh,
say.
that's different from this one. Okay. Thank you.
Thank you. Any other questions? Just one? Yes?
As we know, when we fabricated the titaniums, we have different directions, the scanning speed directions or the longitudinal
Exactly.
directions. So which directions do you
It's
mark on the video?
vertical.
Work?
Exactly.
Okay, I'm just curious about that the result of your ESD. The grain size, do you detect the grain size?
Grain, we have like, no, we have not evaluated the grain size. In that case, we evaluated the lath thickness, alpha lath thickness.
Okay. So thank you again.